Every time a streaming service recommends a new show or you get one of those year-in-review summaries, you're looking at the handiwork of batch processing. It's this silent, incredibly powerful engine that works behind the scenes, making sense of just massive amounts of data. Today, we're going to pull back the curtain and see exactly how it all works, starting with a really big problem.
So, picture this. You've got a log file with a billion entries. A billion? How in the world do you even begin to find the most popular pages? You can't just pop that open in Excel, right? This is the exact kind of puzzle that batch processing is designed to solve. It takes a whole mountain of data and finds that one little needle in the haystack, and it does it reliably every single time.
All right, so here's our game plan for today. First, we'll figure out where batch processing fits into the grand scheme of things. Then we'll take a look at its surprisingly simple and brilliant ancestor, the Unix pipe. After that, we're going to scale that idea way up with something called MapReduce, see how it tackles a really important task called a join, and finally, we'll check out the modern systems that make all of this stuff run even faster.
Okay, so to really get a handle on batch processing, we first have to understand the different worlds data lives in. Think about it. When you click the buy button on a website, you expect something to happen right now. But when that same site figures out its best-selling products for the entire month, well, that's a totally different kind of job that happens later on, offline.
Exactly. So with online services, it's all about speed, or what we call low response time. You're waiting for that page to load, and every single millisecond feels like an eternity. Batch processing completely flips the script. The main goal isn't lightning-fast response time for one single user. It's all about throughput. How much data can you possibly chew through over a period of time? It's about efficiency at an enormous scale.
And, there's actually a third player in the game, stream processing. You can think of it as a kind of hybrid. It's got the scale of batch processing, but it works on data in near real time, as it's happening. We'll get into that another time, because honestly, to really understand streaming, you've got to nail down batch processing first.
Now, you might think the core ideas behind all this big data stuff started in some massive data center at Google or Amazon, but the real philosophy started decades ago with a simple, absolutely brilliant idea built right into the Unix operating system. So let's get our hands dirty and go back to our big problem, finding the top 5 most popular pages from that giant log file. Believe it or not, we can solve this with a few standard Unix tools, all chained together in a single line of code. Now, I know it looks a little cryptic, but trust me, the logic behind this is just incredibly elegant and powerful. Okay, let's break it down. First up, cat access.log. All this does is read the file and dump its entire contents out. But instead of going to your screen, the output is piped directly into our next command, awk. Think of awk as a precision tool. It can look at each line, split it up into columns, and we've told it to just print out the 7th column, which in this case happens to be the URL our user asked for. Now this next part, this is the absolute genius of the whole thing. The huge list of URLs we got from awk now gets piped into sort. By sorting the whole list alphabetically, we force all the identical URLs to be right next to each other. And that perfectly sets up the next command, unique-c, which can now just zoom through the list, count up each group of identical lines, and spit out the total. We are so close. The output from unique is a list, with the count first, then the URL. So we pipe that into sort again, but this time we give it a couple of special instructions. N to sort numerically, not alphabetically, and R to do it in reverse, so the biggest numbers are at the top. The very last step, head-N5, just chops off everything but the top 5 lines. And boom, there's our answer. And that right there, that perfectly captures the Unix philosophy, as described by the guy who invented pipes, Doug McElroy. You build small, simple programs that each do one thing really, really well. And the pipe, well, that's the garden hose that lets you connect them together in any combination you want to solve much bigger problems. So that garden hose idea is fantastic. But what happens when your data isn't in one file, but it's petabytes of data spread across thousands of different machines? Well, you need a fire hose. And that, in a nutshell, is MapReduce. It's the same exact philosophy, just blown up to a mind-boggling scale. The first piece of the puzzle is the map step. A program called a mapper goes through every single piece of data you give it, and its one job is to pull out a key and a value. Sound familiar? It should. It's doing exactly what our awk command did. It went through each line and pulled out the URL to use as our key. And the second piece is the reduce step. After the mappers run, the system automatically collects all the values that have the very same key, so all the identical URLs, and sends them all to a single reducer. And the reducer's job? To process that one group. In our Unix pipeline, that was the job of Unix-C. It took all those identical URLs that sort put together and gave us one final count.
Okay, so this diagram shows how it all comes together. First, your input data gets split up and sent to a bunch of different mappers that all run at the same time, in parallel. Then comes the magic in the middle, the shuffle. This is where the framework automatically gathers up all the key value pairs, sorts them by key, and makes an absolute guarantee. All the values for any one key will end up at the same reducer. Then, the reducers also run in parallel, each one working on its own little chunk of data. The most important thing to get here is that you, the programmer, only have to write the map and reduce logic. The framework handles all that messy, complicated shuffling for you.
So counting things at a huge scale is cool. But one of the real superpowers of batch processing is its ability to take two completely separate, gigantic data sets and join them together to find new insights.
Check out this classic scenario. On one hand, you've got this enormous log of user activity. Every click, every page view, all tied to a specific user ID. Then, in a totally separate database, you have your user profiles, their age, their location, again, tied to that same user ID. The challenge is, how do you combine these two worlds? How can you answer a question like, what age group is most active on our website?
The solution is just beautiful. It's an algorithm called a sort-merge-join. Here's how it works. You run mappers over both of your datasets. And for both datasets, the mapper's job is to pull out the user ID as the key. Now, because that magical map-reduce shuffle guarantees that all values for the same key end up in the same place, a single reducer will get everything for a specific user. It'll get their profile information and all of their activity logs. From there, it's easy for the reducer to combine or join them. It's an incredibly clever way to bring related data together, even when it starts out billions of miles apart.
Now, MapReduce was, and I mean this, a total game changer for the industry. But it wasn't perfect. It had one big, clunky inefficiency that really paved the way for the next generation of even more powerful batch processing systems. So what's the catch? Well, if you have a workflow with multiple steps, the classic MapReduce model writes the entire output of one job down to disk before the next job is even allowed to start reading it. This process is called materialization. Think about it. Writing terabytes of data to disk and replicating it for safety is slow. It just is. This is where the whole paradigm shifted from chains to flows. MapReduce is like a chain of totally separate jobs, and writing to disk is like the slow truck that has to move all the parts from one factory to the next. Modern data flow engines like Apache Spark, Tez, or Flink see the whole thing as one single coordinated workflow. Instead of writing everything to disk, they stream data directly between steps, right in memory. It's like they brought back the original spirit of that super efficient Unix pipe. And the advantages are huge. I mean, first off, just by avoiding all those slow disk writes, things run way, way faster. These newer engines are also a lot smarter. They only bother sorting data when a step actually requires it, unlike MapReduce, which sorted between every single map and reduce. They make better decisions, and honestly, they're just way more flexible and powerful. But here's the thing. Even with all these incredible new advances, the fundamental idea, that core philosophy, hasn't changed one bit. From that simple one-line Unix command to a complex job running on thousands of machines in Spark, the idea is the same. Take a massive problem, break it into smaller pieces that you can run at the same time, and use a smart framework to bring the right data together to get your final answer. So batch processing is this amazing tool for looking back, for making sense of the past using huge, bounded sets of data. But what happens when the data isn't a file that has an end? What if it's a constant, never-ending fire hose of information? What do you do when you need to process the now? Well, that sounds like a topic for another day.